In this video, we're going to talk about how we use infrared spectroscopy or IR spectroscopy to identify molecules, much in the same way that we talked about how mass spectrometry can be used. So we're still talking about how chemists use techniques to identify substances after they've been through separation techniques. IR spectroscopy is also a very modern technique and still used by chemists today. It's very quick to do. And I just want to show you how you interpret an IR spectrum. So if we start off by looking at this big reference chart at the top here, it shows us a scale of what are called wave numbers on the x-axis versus really just intensity. It's not even on the graph here. It's not important to know where those wave numbers come from. I just want you to get a sense that different types of things show up at different wave numbers. Well, what does IR spectroscopy tells us? It tells us the types of bonds that are present in a molecule. So this works for covalent bonded molecules, so organic chemists use this all the time. And different types of bonds show up in different regions of an IR spectrum. The most common ones are shown here off to the left, and this is pretty much all we're going to look at, and this is what you would learn in a typical organic chemistry class as well. There are many other types of bonds that show up in a spectrum, but they tend to crowd one another, and it's hard to distinguish what's what, so not all chemists use this right-hand version, especially in an undergraduate level class in organic chemistry. This is actually called the fingerprint region because it can be used to identify a specific molecule if you have its known spectrum, but like I said, we're just going to focus on what's on the left here. So you can see the little circles, how this reference chart works is these little circled sections show what bond shows up at each wave number. So an OH single bond would show up rather high in like the 3400s or so. It could be lower than that if it's attached to what's called a carboxylic acid, but otherwise know that those two are essentially the same bond. And it's drawn very low on this graph to mean that if we saw this in a spectrum, it would actually look like a very large dip like that. Infrared spectroscopy gives things where the peaks are upside down, and they're still called peaks, just like you see down here in the example we'll get to in a second. The peaks are these troughs that dip down from the top. So an OH stretch, it's called, would look like this with a very broad, deep peak as a result. Other types of bonds that we see are things like the NH bond, and then we have CH bonds. There's a variety of them. They're not usually as broad. They usually tend to be much sharper. So I might see something at around 3000 for a CH peak that would look like that, a very skinny dip in the spectrum. And that's very different than the broad stretches you see. And then you get to the carbon-carbon triple bond or carbon-nitrogen triple bonds. These triple bonds will show up at around 2200 wave numbers, followed by some double bonds, a carbon-oxygen double bond or a carbon-carbon double bond down in the 17 and 1600s. So how does this work? Let's take a look at an example of a known molecule and just see if we can make sense of the spectrum. Off to the left I have an example of what's called a ketone. This is cyclopentanone. And I'm going to zoom in really quickly and highlight there's only a couple of bonds present in this molecule. We have a CO double bond, we have lots of CH single bonds, and then we have lots of CC single bonds. And that's it. I have multiples of some of them, but those are the only different types of bonds, and we can see them in the IR spectrum. So we zoom back out and look at the entire thing. Most IR spectra are red left to right, and the first thing I see is this set of peaks right here at around 3000. Well, if I look at my reference chart, that could be anything on the left-hand side here, but I know the molecule only has those three types of bonds, so which is it? Well, it must be the CH single bonds. That's not where COs show up, and that's not even where CCs showed up. We didn't even mention those. So this must be the CH bonds, and apparently they're not all identical, and I see at least two different peaks there. Continuing from left to right, the next main stretch I get to is this peak at around 1750 or so. And looking at my reference chart, that's my CO double bond. So that tells me that this molecule has that ketone present. That's what a CO double bond is called in this case. And if I didn't know the structure, I would easily recognize that from an unknown substance that that's a ketone. Now past that, we get to this range that's anywhere from like 1500 and below. And this is where we get to what's called the fingerprint region. And while it has many peaks in it, it's so unique for each molecules, it's not as descriptive for someone that's just starting to learn how IR spectroscopy works. So we're actually not even going to address the rest of these peaks. Clearly there are carbon-carbon single bonds in there, and then you might be saying, well, why are there so many others if there's only 3 different types of peaks? Well, different bonds, when they're connected to one another, for any bond between one atom and another, are not as rigid as you might think they are when we draw them. They can stretch back and forth, they can wiggle, they can vibrate, they can rotate, and all of those types of little transformations involving the covalent bond absorb different types of energy in the infrared region. And that's what we're seeing in the fingerprint region primarily, which is why it gets so crowded. Okay, so let's take a look at a few other examples. I have 4 molecules that you should recognize from the mass spectrometry video. We have our amide, our ester, the nitrile, and the ketone. I'm just labeling them so that we can refer to them more easily without having to draw the entire molecule again. And down below are 4 different IR spectra, and each one goes with one of those molecules up above. So let's zoom in and try and identify which one is which. Here's the first one, spectrum A. If I read it left to right, the first thing I see are these peaks here at around 3,000 or so. And those, as we just had in the previous example, correspond to CH single bonds. Moving forward, I have something else that looks very similar to the previous example. I have something at 1700, very broad. That's probably a CO double bond if you look back up at the reference chart up at above. And then I really don't look at much beyond 1500 because that's where you get to the fingerprint region. I know we're seeing a couple of small peaks down here. Those are due to some of those other vibrations that we get in an IR spectrum. It's really the broad and sharp peaks that we look at. So looking at the molecules up above, which one only has CH bonds and CO double bonds and nothing else that should show up in the IR spectrum? The first one has those bonds, but it also has CN bonds and it has NH bonds. And if I remember correctly, the NH bond is actually quite characteristic, showing up very far to the left in the spectrum, above, looks like 3200 or so. So I should see something in the upper 3000s for this first example, and I don't really see a whole lot over here to the left. So I don't think it's the amide. This one happens to be the ester. There's nothing else interesting in the spectrum other than that CO double bond and that CH bond. So I want you to hit pause and try and do the other 3. Just match which one goes with which and see if you can identify a couple of peaks that prove why it's that spectrum. Okay, so let's take a look at the next one. The next one has pretty sharp peaks. The first one that stands out the most is this 3000 here. Also this 2200 is pretty unique. At around 3000, I'm thinking it's probably a CH bond, and then in the 2200s, if I look back up at the chart up above, that's a C triple bond something, either a carbon or a nitrogen based on that reference chart. And if I look at the examples, the only molecule of the remaining 3 that has a triple bond is the nitrile right there. So I'm already suspicious that this is the nitrile and that that's the C triple bond N peak as a result. And if I look well above 1500, I have something right at 1600, and that's carbon-carbon double bonds, and then the rest of it I don't really pay attention to because it's 1500 or below. And those are the 3 things that I should see for the nitrile. So this is the nitrile, really indicated by that triple bond. Continuing down to the next one, part C, I have a very busy mixture going off on the left here, not just at 3000, but well above 3000. And if I look back at the remaining two examples, this is either, OH or NH bonds based on the references, and none of our examples have OH bonds, so this must be something that contains an NH, and then that pretty much gives it away. This must be the amide. And if I try to make sense of some of the rest of it, at around 3000 I have a CH single bond, and then at 1600s, high 1600s, I guess I have a CO double bond. 1600 might be a carbon-carbon double bond, but I don't have that in that amide structure. So it's sort of a combination of using the peaks to figure out the molecule and then using the molecule to figure out what the peaks are, going back and forth when it's this kind of matching exercise. And once again, we're not really going to pay attention to the fingerprint region in that. And that just leaves one more spectrum, which is really the least interesting spectrum. This is the most boring of the four. The only thing I see that's outside the fingerprint range is this 1800, which I guess is a CO double bond, and that must be the ketone, the only remaining structure. And it makes sense why there's nothing else in this region, because I have no hydrogens in that molecule. So there's no OHs or NHs, there's no CHs, and apparently there's no triple bonds either, so it's just the CO double bond. So that's how you use IR spectroscopy to interpret what different types of molecules are. It shows you what types of bonds are present, and the fingerprint region can be used to identify a specific molecule, but for our purposes we're just going to look at examples where the most common types of bonds show up in the molecule, and that's how we'll use IR spectroscopy.